what can be a good example? So for speech, let's say, when I'm talking and you record the audio, what is the feature like which discriminates my audio from his audio? Normally there are some features like MFCCs or some other things, but let's say we don't know. Okay, we try to model the ear, but maybe it doesn't work well. Maybe we don't know the real feature. Like, what is the real discrimination? We gave apple and banana very basic things, but in real machine learning examples, you have very complicated scenarios, like where you cannot find out that, okay, you will really know that, yes, this thing is different from this thing, but you can never come up with the feature itself, like, okay, what should I use? Oh, can you come up with some nice example? I don't know.
All of the example is images.
Images, for example, like, for example, how will you know that, okay, this image has a cat inside it or not? I mean, cat can be a lot of different cats, and then, so what did, there was this famous task like Google Brain project, where they were feeding the algorithms just the videos from YouTube which contains cats. And later it learned itself that, okay, they didn't tell him that, okay, there is a cat or not, or what are the features or whatsoever, but they were feeding the data. Okay, go, try to find something, and it learned that, okay, it has something in common, and it tries to find out that feature itself. You see the point?
Yes.
So neural networks are more engineered for this kind of problem.
To predict a feature, kind of.
To extract the features.
Extract features.
Or when you don't know that, what are your features? Like in this apple and banana, this is very simple. Let's say for I will give you more example next time, but think of something like with the speech.
With the speech, yeah.
You don't know what is the difference between my speech and your speech. When I speak, you find it out. So they tried to model the human ear, but then later they found out that I think neural network works even better than MFCCs, I think. And sometimes you even give the features to these neural networks and try to extract or find out, like transform these features into a better features. There are some techniques. So yes, there are ways to find out, like, okay, which algorithm or which problem is suitable for your thing. So that's good question. Yes. So this thing, cross-validation. You know cross-validation now, right?
Yes.
That you divide it into sets with equal proportion of these things, and you do the repeatedly, then find the accuracy for every time, and then you find out, and then you do this for a range of values. Let's say for SVM we have C and gamma. So you have like C 0.1, 0.2, 0.3, blah 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 to something, and C is equal to 0.1, 0.2, and you try the combination of this with this because they are hyperparameters. And try all these setup. I have the codes and I can explain maybe next time. You can do it very easily in libSVM as well. They're like, you find out the indices, and once you make the experimental setup.
Okay, I have a question. It's basically the same question I asked the last time. After doing this on so many variations of C and gamma, you will get, for example, one C and gamma as the best ones. Okay, that's the problem when you did it with, for example, n-fold. If you do it with 8-fold, do you expect to get different C and gammas? Really different C and gammas?
Not completely different, but it's possible. I will explain one more setup, like how is this experimental setup done.
This is my problem right now.
So let's say you have this data, okay?
Yes.
Yes. And imagine you extract, first of all, you will divide it into 70-30 thing. This 70 is your training data.
Yes.
And this 30 is your test data. Now you will forget this 30%, because this is where you test the final results of the algorithm, or finding the final result of the algorithm. You do the 10-fold or 8-fold cross-validation on this 70%. So the 70% comes here, and you do 8-fold, 10-fold, whatever fold. Yes? So this.
I think Akira might have gotten the time right.
Hello.
I'm sorry.
I think
You are very late. We have
1
certain.
hour late, professor.
Yeah, because because I was cast to the visit to the
Ship.
boat.
Oh, yeah?
Yeah.
Okay.
Just, you can
So-
sit there if you want.
Special seat.
But the 70-30, there is one more trick in this. Because you select these randomly,
Okay.
but keeping in mind this percentage, like 70-30% is also the percentage of the labels.
Okay.
And you do it, for example, 5 times. So you will have, let's say this was your original data set. So you will have 5 copies of this. Copy 1, 70-30, copy 2, 70-30, copy 3, 70-30, copy 4, 70-30, and 5.
Okay.
And you keep the track of each copy that, okay, for this copy, this was my 30% test. For copy number 2, this was my 30% test. For copy number 3, this was my 30% test. And you do this 70% here for each copy, you remember that which was the corresponding one. And what you do is, you do the cross-fault validation here. And here you find the best C and gamma. And this is your hyperparameter. And you use exactly this C and gamma which you find for this 70% to test on this 30%. And you get the accuracy. And for the another copy, you get this thing, you find the C and gamma, and you don't care. You just find the best C, and you find the best C and gamma, and you put it for this test. So it's for sure that you will not get exactly the same C and gamma.
Not exactly, but
It's fine. It's different.
I'm actually getting too much difference. Something
It's
like
okay.
Too much difference.
32 and 8,000.
No, this is the problem in the kernel, I guess.
Kernel.
Yeah.
I mean, in my case, I most of the time get this difference, but since it's the hyperparameter, you have to optimize it.
I didn't
RBF
understand
kernel
what
is
you were
Gaussian.
talking about.
I will explain this maybe
I know.
next time in detail.
Don't worry about that because sometimes you have to change the kernel.
But
Okay.
I think I will look into this. But
If
you,
start really
but this is the basic idea that okay, you always find these hyperparameters here and go back and test on those 30, and then you get. Some people will report this as accuracy. This is cheating.
Yes.
This is clear cheating that you cannot report the accuracy on the training set
Yes.
because you are doing this thing and you know that okay, this is the best one. This is the real test that you go back here, do the test, and then for all the copies of this thing. This is like what I was told or what was explained to me recently very nicely. Are we missing something now? Okay, accuracy. Why accuracy is not a good measure? How you measure accuracy?
I thought accuracy is for classification problems.
Yes, but why is it not a good way to measure accuracy? Why is it not a good metric to measure accuracy?
What is it? Not measure.
Accuracy is the number of
Error.
Correct.
correct ones
Yeah. no.
divided by total instances, right?
Yeah,
Yeah.
yeah.
Why is it not a good measure? Tell me.
Here you are talking about accuracy which you measured for just the test set, not for the whole test.
I will explain why. So
Why they use it if it's not good?
then they have better matrices.
there is-
Yes, it is better matrix.
I thought it's the latest one.
This is very basic, right? So let's say you have a data set, okay? Let's say you have a data set. And let's say you have 95% label 1. 95% label 1.
Hello.
You're in the middle of the day.
We're just finishing.
No, it's all right. Firas, you need me for something or not?
Yeah. I will.
I'll be in my office, so call me later.
Okay.
Okay. Finish up.
So let's say this is the 95% is from label 1
Mhm.
and 5% is from
Label 2.
label 2.
yeah.
Okay?
Yeah.
And imagine that this classifier is very, what was this keyword for this?
Naive.
Like it's always classifying everything to 1.
Exactly.
Everything to 1. Everything to 1.
The accuracy would
So
be
what is the
something
accuracy?
Like 95%.
1.
95%.
Yeah, 95%.
95%. But it is never detecting this guy. And let's imagine that we have a case for predicting cancer in a guy. So it's always predicting that every guy is healthy. Every guy is
And
healthy.
it is only 5 choices.
But the accuracy is like 95%. 95%, but not a good measure. So then we come up with like precision, recall, true positive rate, true negative rate. I think I will skip the basic ones. I will just skip to the ROC curve. ROC, receiver operating characteristic curve. An area under the ROC. Okay. I used it a lot, and we can talk about ROC a little bit, and then we can finish this one, and if we agree on something, then we can continue this in the next sessions as well. Okay, the normal machine learning model, it always gives at the end some threshold, like some value on the basis of which you decide the threshold that, okay, if it's more than this, I will assign it level 1. Like, remember what we did in the machine learning in the beginning, like some probabilities, let's say, okay? So, for example, for one model, this values has some threshold values behind, okay? So this is one model, but I'm just taking decisions. So for this point, for this threshold, it's giving me this false positive. Let's say this is 0, 0.2, 0.3, 0.5, and 1, and this is the same 0.2, 0.4, 0.5, 0.6, blah blah blah. Okay. Now they say that this is a kind of okay, or there can be better measure as well. I don't know, but for me this is a really good one to find out the accuracy of the model. And that is when I plot my classifier like this, and there is one more like this, but we cannot really see which one is okay. Of course we can see that, okay, if we choose this threshold for this model is better, but normally they think of it as the area under the ROC curve. So the model with greater area under the ROC is good one normally. There is one more term as well, I will explain why, but normally this is the way. And what was true positive rate and false positive rate? You all know, or I can explain. It's you know, right? True positive is that it was predicted true and actually it was true. It was class 1 and predicted as class 1 as well. And what is false positive? That it was predicted
0, but was predicted
But
as
it
class
was.
1.
Yes, and we use these kind of measurements for normally when we are focused more on detecting one specific level. In this case, let's say true positives or positives. Like we want to try to find out the patient who has a cancer. So which one can be a better model? But then there is one more term which I found very interesting, is that in ROC curve, they normally use partial area under the ROC curve. And partial area is that you don't care about the whole area. And I have printed one example. I will try to, okay, maybe you can see here. So this red and blue one, they both have almost the same area under the ROC curve. But which one is better?
I think the blue one.
No.
No, the red one, because it is
Red
better
one.
at the less
Beginning?
false positive.
Yes, and I will explain why. Because when you go towards this direction, it's 1 minus specificity, it's false positive rate. So we want to have the false positive as low as possible. and we want to have sensitivity, which is the true positive rate, as high as possible. So we want the classifier to have something like very close to this part.
Oh, I see.
So you see, so for example, if I choose this part, so it has very less false positive. False positive is not good, we want to reduce false positive. And very high sensitivity, true positive, right? So this is good. So then they think of it that, okay, maybe we should consider partial area under the ROC. That this area, in whichever is rising high, will have more area, so then that's a good classifier.
What is the true limitation? I mean, towards what false positive they take these?
Depends on the problem. Like for example, when I was working on this project, I explained it. I don't know if you remember, if you guys remember. Like we were trying to detect the trains in Netherlands. So we had trains. Like we have an audio sensor in the field, and we want to find out that, okay, from the audio, is the train going? Is it a train or not? So for non-trains, we have like scooter and cars and some guy screaming or some truck is going by. And for train, it's only train. So for the guys, that okay, because we can have a lot of false alarms. But if it says that it's a train, it should definitely be a train. We can miss some trains, okay. But if it says that, okay, we should have like a very strong. So what they wanted to have is a very high true positive rate. Because when they see that, okay, in the system, because there are like every 5 minutes there is some event coming. Of course, they cannot afford like having these alarms always. So they said that, okay, we might have some problems, but when it says that, okay, this is a trend, it should definitely be a trend. So they were looking for something at very high peak on the true positive rate side.
Because it's going to be dangerous otherwise, right?
So they wanted to have like, so it really depends on that problem. Like, for example, for the cancer patient thing, I don't know what can be the good thing, but think about this. Like, it's really application specific.
Yeah.
And these thresholds are decided like, okay, what we want, what we don't want. But normally these kind of problems are for binary classification.
Yes, and do we have another metric that can take into account false positive and true negative?
I think it's precision, right? So precision is true positive, false negative. And then there is F1 measure as well, which takes into account these things.
Okay.
But this is just to give you like a basic gist of why accuracy is not a good measure.
So I have a comment that
Sure.
Anyway, with my chair.
Special seat.
So the evaluation system is performed sometimes using the ROC curve, but in practical applications, one of them is limited by the, for example, the admissible rate. For example, the false positive rate should be less than 0.2, and the 0.2 is limitation, admissible limitation.
Yes.
So that this
Yes.
kind of partial method is used for practically. In my experience, when I worked for the analysis of radiograph, dental radiograph, and I and my colleague, he is a Japanese radiologist in Dental University, and I and my colleague had a negotiation with the Finnish dental equipment company, but we failed this negotiation because the philosophy is different. Japanese people say that the true positive rate should be high. We shouldn't miss any candidate or suspected disease.
But the others say
Yeah, but it
Finnish
depends.
company says
Yeah.
we shouldn't
This way, yeah.
we should
Choose-
suppress
Yes.
the false positive.
Yes. So it really depends on the application and the requirement of particular client, let's say, or whatever. Yeah. So let me see if we are missing something. And okay, I think it was good to have you guys here. We'll finish it now. It's weekend, and then maybe we can continue.
unfortunately you came too late.
I'm sorry.
Well, it's okay. Maybe in the next session I will just give a brief overview in a very
Okay.
short time. By the way, we were recording the video, so maybe I can give you the video.
Yes, we
Is it
have
still
recorded
recording?
the video.
Oh.